Hello everyone, welcome to the online lecture series of the course EE204 Digital Electronics and Logic Design, Module 5 Synchronous Counters and State Machines. Today we are going to study about a special type of counter called as ring counter. A ring counter is a synchronous counter having lesser number of valid states. For example, if we are taking 3 number of flip-flops in the design, the counter can have a maximum of 8 valid states. So with a 3 flip-flop, a ring counter circuit will be having only less than 8 states. To be precise, the exact value is 3 itself. We can construct a ring counter either by using a D flip-flop or by using JK flip-flop. If you are using D flip-flop, the connection will be just like a ring, which means the output of the first flip-flop will be connected to the input of next flip-flop, and this pattern will continue. And in order to make a loop, we will be completing the loop by connecting the output of last flip-flop as the input of first flip-flop. The same way you can construct a ring counter using JK flip-flop also. Here the J and Q will be connected to form a ring, and similarly K and Q bar will be connected to form a ring. That is, the output of first flip-flop Q will be connected to the J input of next flip-flop, and the output Q bar of first will be connected to the K input of next flip-flop. This pattern will be continued, and now to make a loop, the output of last flip-flop Q will be connected as input to the J of first flip-flop. Similarly, the output Q bar of last flip-flop will be connected to the K input of the first flip-flop. One important point to be considered while designing a synchronous counter with lesser number of valid states is the lockout condition. We have to make sure that the counter is not going into the lockout condition. A lockout condition is such that the counter may eventually fall into a invalid state, and it will not be coming back from the invalid state to a valid state. So which means once the counter has gone to an invalid state, it will not be returned back to a valid state. This is just like you are writing an infinite loop in a C program. One more point to be noted in the case of a ring counter circuit is that the counting sequence of a ring counter is just like this. Adjacent flip-flop outputs in a ring will be either set or reset. For example, if you are having a 4-bit ring counter, if let's say first flip-flop is set and the remaining 3 flip-flops are reset. So on each clock pulse, this set flip-flop output will be transferring this 1 to the next flip-flop, and this pattern will be continuing. That is, if the initial output is 1 0 0 0, the next output will be 0 1 0 0, next output will be 0 0 1 0, like that pattern will be continuing. So the problem is that the flip-flop output must have at least one set condition. Since all the flip-flops are initially in the reset mode, that is 0 0 0 0 in this case, this flip-flop will not be self-static. So you have to manually set the initial state or any valid state in the ring counting sequence. Since a 4-bit ring counter will be having only 4 valid states, that is, the number of states will be equal to the number of flip-flop you are using in the circuit. A 4-bit ring counter circuit is called as a mode 4 ring counter circuit. A ring counter circuit is also called as divide by n counter, where n is the number of flip-flop. So we can see in this state diagram the 4 states 1 0 0 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. They forms a loop, and the state 0 0 0 0 that can be observed only once in the entire operation, that is at the time of starting only. Once the counting sequence has initiated, then we will not be see this state further. So that is why the state 0 0 0 0 is not part of the ring. So here we are using a D flip-flop to set up the ring counter circuit. So you can see the excitation table of D flip-flop as shown in the table. Now we have to complete the design table. Since there are only 4 valid states, your design table will be having only 4 rows of data, starting from 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. Next you have to complete the next state column. Once you have completed the present state and next state, then you have to obtain the input of each of the flip-flop by comparing the present state and next state of the corresponding flip-flop and using the excitation depth. Here you have to note that there are only 4 valid states and remaining 12 states are invalid states. So at the time of K-map simplification, we have to treat these 12 invalid states as don't care terms. On the left side, we can see the K-map for dA. On simplification, dA is obtained as QD. On the right side, we can see the K-map for dB, and on simplification, dB is obtained as QA. On the left side, we can see the K-map for DC, and on simplification, DC is equal to QB, and on the right side, we can see the K-map for DD, and on simplification, DD is obtained as QC. Using the minimal Boolean expression for each of the flip-flop input, we have to complete the logic circuit diagram, and the completed logic circuit diagram is as shown in the figure. So in order to understand the working concept of a ring counter, let's have a simulation. So you can see a similar circuit as shown in the previous slide. Here, in order to check the asynchronous inputs, they are split into 2 sets. The first flip-flop, we have alone provided a separate connection, and for the remaining 3 flip-flops, we have a common connection. This first flip-flop alone we are going to set in the ring counter. So this set condition will be transferred to the next flip-flop on obtaining a clock pulse, and this process will be continued. So let's check the asynchronous inputs first. So making the high value to 0, we can set the flip-flop, and preset value to 0 will set the first flip-flop. So now I'm going to clear the flip-flop outputs. So making clear to 0 will reset all the flip-flop output. So now just apply few clock pulse. So on the first clock pulse, there is no change in the flip-flop output. You have to remember the concept that I have already told. The counter is not self-starting. So from 0000 state, the circuit will not change its output even if you apply clock pulse. So now to start the counting operation, we have to manually set the counter to its initial state or any valid state. So I'm going to set the first flip-flop, so that is the counter output is set as 1000. Now on application of clock pulse, we can see that the first flip-flop output has shifted to second flip-flop, and the counter output thus becomes 0100. On the next clock pulse, the counter output is 0010. And the next clock pulse, the counter output is 0001. And the next clock pulse, the counter will come back to its initial state, that is 1000. This will continue on obtaining every clock pulse. Now drawing the timing diagram, initially the flip-flop outputs are set to a desired value, that is 1000. So at the end of first clock pulse, the counter output changes to 0100. On the second clock pulse, the output changes to 0010. And on the third clock pulse, the output changes to 0001. And at the end of fourth clock pulse, the output returns back to its initial state, that is 1000. So I hope with this explanation and simulation you have familiarized the working and the concept of a 4-bit ring counter circuit.